This is a broad overview, and we're assuming that you've had some kind of extensive ground school in 727 systems already. Otherwise, it would kind of be like trying to get a drink from a fire hose. Okay? Obviously, anything we say here that conflicts with your own airline's procedures or schematics, remember this is only for training, and the airline books take precedence. Okay? Now, since we're talking systems, we're going to start discussing the basic systems, which would be those contained on the 727 second officer's panel. And over here we have a second officer's panel, and we'll just start in the upper left-hand corner with the electrical system. The electrical system, as you know, is composed of 3 115-volt AC generators powering 3 AC buses. And in addition, we have an essential AC bus also, which can get its power from one of many sources that we'll discuss. Let's talk just about one generator for a minute. Basically, the on-off switch for the generator is the field switch. The field switch, when closed, allows generator output to go up to a point schematically shown right here, right at about the head of that screw, which we'll talk about a little later. And then the output of the generator can be tied into the respective AC load bus through the generator breaker, the GB. Now, whatever's powering that load bus can also be tied to other load buses through the bus tie using the bus tie breaker switches, one for each set of generators. The generators are turned by the engine through a fluid coupling, which we call the constant speed drive, and we have a temperature gauge to tell us how the temperature is doing on that constant speed drive so that we can see if it's generating too much heat, and we can also determine if we have any kind of generator malfunction. Now, just above the CSD temperature gauge, we have a toggle switch, which is capped and guarded, and that's used to disconnect the generator drive from the engine in case we have some kind of CSD or generator malfunction. The low pressure light right next to each switch tells us of low fluid pressure, low hydraulic pressure in the fluid coupling. Now, it's important to remember that this switch is an emergency type switch only, because once we disconnect the CSD, the constant speed drive, we can only reconnect it back on the ground. You'll notice now that we have a button here that says rise, and some airplanes have a toggle switch. When we press the button, instead of reading the generator CSD temperature leaving the CSD, the out temperature, we get a measure of how much the temperature has risen going through the CSD. That is, we're really measuring the in and the out temperatures, and we're comparing the two. Now, you can see that this temperature gauge is labeled rise on the upper scale and out on the lower scale, and we've got a button that we press for rise. Or on the older aircraft, the gauge is labeled in on the lower scale and rise on the upper scale, and we have a toggle switch that we can position to either in or rise. Now, really, regardless of which type of gauge we have, we're getting the same information. The out temperature on the newer airplanes is the temperature of the hydraulic fluid, the oil leaving the constant speed drive. And the rise is a measure of out minus in temperature, the difference, that is to say, CSD workload. On the short-bodied airplanes, the in temperature is a measure of the temperature going into the CSD, so really it's a measure of the oil cooler efficiency. But in either case, the limits are really the same, and that is to say we can have a temperature rise of 20 degrees, and we can have a maximum temperature out of 130 degrees. And of course, on the short-bodied airplanes where we only measure the in and the rise temperature, then in plus rise would equal out, and that could not exceed 130 degrees. Let's take a look at the switches that control each generator now. We'll concentrate on the center one here, the generator for the number 2 engine. You notice at the very bottom of our picture we've got the kW, kilowatts meter, and that's telling us the electrical load in terms of kilowatts that the generator is handling. Then we've got the field breaker, the FB, which, as I said, is the on-off switch for the generator. And then above that is the generator switch, and the generator breaker controls the output of that generator to its respective load bus. And then the bus tie breaker above that, which would allow the generator for any particular side to be tied into the generators, the other operating generators. If we use the bus tie breaker for paralleling, which is tying the generators together, we're going to have to do it manually. And there's, of course, a procedure in the book to tell you how to do this. But the important thing to remember is that the generators have to be exactly in phase when you manually parallel. Otherwise, you'll actually be trying to motorize one generator with the output of another generator, and you'll probably end up with a shared generator shaft. You'll notice just below the generator breaker there's a small screw, and we call that the essential screw. And that is because regardless of whether or not the generator breaker is closed, we can draw essential power from that generator if the field breaker is closed. Now, I know you're probably thinking an essential screw is something completely different on long layovers, but for 727 electrical system purposes, we'll call this the essential screw. We'll see how this ties in when we talk about the essential AC system. If we use the generator breaker for paralleling, we have automatic paralleling protection, and we can close the generator breaker switch at any point in the electrical cycle, and it will wait until the generators are completely in synchronization before it closes. So that's the automatic paralleling protection feature. Now, we've already discussed that using the bus tie breaker, we use what we call manual paralleling. Using the generator breaker, we have what's called automatic paralleling. Well, how do we manually parallel? Very carefully. We have to observe the synchronizing lights, which are in the lower right-hand corner of the electrical system. And these will be blinking together. And when they are blinking, they are reflecting a difference of cycle, a difference of phase between whatever you have selected on your AC meter switch and whatever is powering the tie bus. So if we have 2 generators already tied into the tie bus, and we have the 3rd generator, we'll say generator number 3, which we would like to manually parallel to the tie bus, we select generator number 3 with the AC meter selector, and now when the lights are on, it means that generator number 3 is not in phase with generators 1 and 2, which are paralleled on the tie bus. And we have to wait, as we said, until they're completely in phase, or else we stand a problem of shearing a generator shaft. And so what we will do is we will adjust the frequency, the output of generator number 3 with the frequency selector until the lights blink at the very slowest we can get them. And when they are off, that is when they are in the midpoint of their off cycle, we will close the bus tie breaker, and that will parallel the generators. Once again, if we can't do this, if we could never get a slow enough frequency so that we felt confident and comfortable that we could manually parallel, one thing we could do would be to open the generator breaker, close the bus tie breaker, because we would not have to manually parallel if there were no conflicting power source vying for the attention of bus number 3. And then we could quickly close the generator breaker and let the automatic paralleling sequence take over. And that's what's called chicken paralleling, if you want to call it that. The only disadvantage of that is that we would leave the number 3 bus unpowered for maybe a second or 2. So it wouldn't be something that you'd do without discretion, and of course you'd clear it with all the other members of the crew before doing it, because it would leave some equipment unpowered. But in turbulence, or when you can't get the lights to blink very slowly, that would be a way of getting around the problem. So let's look at what we've got so far in terms of the electrical system. We've got 3 generators, each going through a field breaker, which serves as the on-off switch for the generator. And then the output is to the respective load bus is controlled by the generator breaker. And then we can tie all 3 load buses together through the bus tie breakers. Once again, manual paralleling, automatic paralleling. And we can monitor the voltage and frequency of each generator just downstream of the field breaker. So once we turn the generator on, we can check the voltage and the frequency. And of course, that would be necessary to make sure that our generator is within limits prior to placing the load bus on the generator, because then if we did not have proper voltage and frequency, we could do some damage to some electrical equipment. Okay, is that the entire AC system? Well, of course not. We've got some equipment that's more important than just your run-of-the-mill everyday equipment that you find on buses number 1, 2, and 3. And we call that essential equipment. So we have an essential AC bus, and it can be, we'll just draw it over here, and we'll make it appear bigger. This is our essential AC bus, and it can be powered from one of many different sources, okay? But it can be powered from any of the 3 generators for sure, and like I mentioned before, the generator does not even have to be powering its own load bus. The generator can be sitting there powering only one thing, essential power. So we have a way of selecting with a wafer switch, selecting where essential AC will get its power from. And whichever generator we choose to take it from, then we are drawing that power directly from there, the essential screw. So it's important to remember that even if all 3 load buses, number 1, 2, and 3, are unpowered, we can still retain essential AC power. Now we can also get essential AC power from the APU or from external power. When we have selected APU, however, we are not really letting the APU power the essential bus. We are enabling whatever is powering the number 3 bus to power essential power. Here's how it works. When we select APU position on the essential power selector wafer switch, the yellow wafer switch, then whatever is powering the number 3 bus will power essential power if we have an interlock here, which we must satisfy. We'll call that a relay. We have to have the APU running and the APU field breaker must be closed. Now, if we've satisfied those 2 conditions, then whatever's powering the number 3 bus will power essential power. Okay, so you could see that, for example, if, as some airlines taxi in with the number 3 engine shut down, if the number 3 engine were shut down, well then the number 3 load bus would still be drawing power from the bus tie, actually powered from generator number 1 and 2. We could start up the APU, not place it on the line, just let it sit there with it running, with the field breaker closed, and we could select APU position on our essential power switch, and we would actually be getting essential power. And then all we'd have to do to shut down the remaining engines and never have an interruption of essential power would be to close the generator breaker for the APU, allowing the APU to power the load buses. It would power the tie bus and in turn all 3 load buses plus essential power. That's a pretty good deal. Also, we have a similar type deal for essential power with a completely different interlock for external power. That's called the EPU, the external power relay. And again, when we use external power to power essential power, whatever is powering the number 3 load bus powers essential power if external is plugged in to the aircraft. Again, external power does not have to be powering the aircraft. We could have generators 1 and 2 through the tie bus powering the number 3 bus, and as long as external power is available, then that interlock is satisfied and we could get essential power. And by taking a look at that, you can see how we can switch power sources and never get an essential power failure indication, which is a red light, a flashing red light on the forward panel, a red light on the second officer's panel, by judicious use of the essential power switch, and knowing that it's what's powering the number 3 bus that's doing it. Okay? Now I'd like to ask you something. What's even more essential than essential power? Right, standby AC power. You know, essential power on the essential power bus are some really important things, but on the standby AC power bus are the even more important things, like the captain's attitude indicator, the number 1 navigation receiver, the number 1 communication receiver. So basically, when you're down to nothing but standby power, you could still fly the airplane. You could fly an instrument approach. You wouldn't get any flight director, but you could still fly a raw data instrument approach. So that is really essential, and we call it standby. So the standby AC bus is powered by the essential AC bus, normally. Whenever essential AC is powered, standby AC is also powered. But because it is so important, we have another power source for it in case we even lose essential AC. And then we can power the standby AC bus from the battery. Now, there are some of you among us who are going to say, wait a minute, the battery is DC. You said this is standby AC. How do we do that? Very good. As you know, we use an inverter will change DC to AC. So this is called the standby inverter, and the DC comes right from the battery bus. And so if not hot wired to the battery, but rather from the battery bus, if the battery switch is on, then we get battery bus power to the standby inverter to change that battery voltage to 115 volt AC, and so we can power all the really, really super important things that are on the standby AC bus. Here's the essential power selector switch we were discussing, and the 5, actually 6 operable positions of this. We can select generator 1, 2, 3, external power or APU, and then we're not getting full essential power, but we are powering the standby AC system by selecting standby. That's what we've discussed so far. Now let's talk about this little red light here. That little red light says we have lost essential AC power. So if we are down to standby AC power, will we still see that red light? If we've lost essential, but we still have standby AC power because we selected standby position? Why, yes, as a matter of fact, we will, because it says we've lost power to the essential AC bus, and in fact, if we go to standby, we have lost power to the essential AC bus. All we have powered is standby AC. How could we tell if we've lost power to standby AC? Sure, check something that's operating on the standby AC bus, such as captain's attitude indicator. Now that red light, as we said, tells us that we have lost power to the essential AC bus. And let's discuss for just a second how that thing works. There is a relay which derives its power from the essential AC bus. So whenever the essential AC bus is powered, that relay is being held closed. Now, if the essential AC bus loses power, the relay relaxes, and battery bus power goes to, now this is a simplification, okay? Battery bus power will go to the red light bulb. And the red light bulb will light up. And that means, hey, we've lost essential bus power. Well, what if instead the relay burns out? What if that wire breaks? What if any one of a dozen things could happen that would make that relay relax, get battery bus voltage to the red light bulb? The red light bulb would light up. Have we actually lost essential power? Well, no, not if there was a problem with that relay or something else. So how could we tell if we have actually lost essential power now, or if it's a phony loss of essential power? Well, what we could do is we could look at the things that are powered by either essential or standby bus, and if they are still powered, we know we have not lost essential power. So what would be the first thing that would come to mind? Sure, the captain's attitude indicator, because he's looking at it all the time anyway, when he's not looking at the Wall Street Journal. So we could look at the captain's attitude indicator, and if there is no off flag in view, it means that the standby AC bus is still powered. And if the standby AC bus is still powered without our having moved any switches, then essential must still be receiving power. And in that case, that's what we call a phony indication, a phony loss of essential power. What do we do about it? Well, there's a book procedure. But what we basically do is we check out the transformer that, you see, this was an oversimplification too, because there's a transformer here. We check out the transformer and the solenoid here, the relay, to see what the problem is. Maybe we're going to have to go through the rest of the flight with a red light on. Or maybe we can fix it. Okay? Well, in a nutshell then, that's our AC electrical system. Now let's talk about the direct current, the DC system on the airplane. And I'm going to have to include just a little bit of the AC system we discussed so that we can see where we get the major portion of our DC power. So here we go. We have a generator and it's providing power, and I'm leaving out all the little switches now just for simplicity's sake, to a load bus number 1. And we have generator number 2 providing power to bus number 2. Okay? Now, in addition to all the things that these buses power, they also power transformer rectifiers. And a transformer rectifier takes AC voltage and changes it to DC. So AC comes in here, DC goes out here. And that in turn powers DC bus number 1, and we have the exact same setup for the number 2 side. We have TR number 2 powering DC bus number 2. So there are a lot of components on the DC buses that are separated to either bus number 1 or bus number 2. And in fact, either one of these TRs, either one of these buses powering the TRs, can handle the entire DC load. And how does it do that? Well, these two buses are tied together through a current limiter device. I call it a fuse. Through some kind of current limiter device, and it might be placed in some arrangement down below the bus so that we could isolate the transformer rectifiers, but we're talking in general terms now. Either one of these TRs can power both DC buses. And how are the TRs powered? Right, from the load buses, the AC load buses. Well, what are the things that are even more important than your basic DC load? Where would they be, on DC load bus number 1 or number 2? Right, they'd be on a bus that we call essential DC. Okay, so essential DC is powered by its own TR, and where do you figure that TR is getting its power? Right, from the essential AC bus. So we've got a parallel type setup here where the essential AC load bus is through a TR powering essential DC. Well, what if there's a problem with the essential AC bus, or more likely, what if there's a problem with the essential TR? Will we lose our power to the essential DC items? No, we won't. There's a way of allowing DC buses number 1 and 2 to power the essential DC bus. And to make sure that we don't get a reciprocal arrangement, to make sure that we don't drain off really important essential DC to power, say, number 1 and 2 if both of these TRs failed, we have a one-way street here, a blocking rectifier, so that the power can come this way, but it can't go back the other way. And once again, as you can imagine by now, anything that's more even important than essential we call standby. So we do have standby DC being powered from essential power also. And then we've got this all tied into what I call the battery bus complex. There are some things called the battery transfer bus, the hot battery bus, the battery bus. I don't want to get concerned with all of those. We'll just call it the battery bus complex. And anytime our DC electrical system is powered, this is powered. Or if the DC electrical system is not powered, but the battery switch is on, this stuff is powered. Okay? So basically now, that is our DC electrical system. Now, how do we know if the TR is working? Well, we can tell if a transformer rectifier is working by measuring the current flow through it. So we hook up an ammeter to the TR, to the transformer rectifier, and then we hook up a voltmeter to the bus. And we can see if we've got voltage on that bus. Now, here's a question for you. What would it indicate if I have voltage, let's say I have good 28 volts on DC bus number 2, but I read 0 in the way of current through TR number 2. What would that indicate to you? Well, it would indicate to you that DC bus number 2 is getting its voltage from DC bus number 1. Because if the amperage is 0, it means there is no current flowing through the TR. So that's the way you tell if the TR is working or not. Current flow. Because unless you lost both TR number 1 and 2, you would not get a 0 voltage reading on the DC bus. Right next to the battery switch, then, we have a DC meter selector which we can put to the battery position to measure the battery voltage. We can put to essential TR position, TR1 or TR2. And when we are in the TR position, we are measuring current on the ammeter through the TR and voltage on that respective bus. Also, while we're looking at this portion of the electrical panel, I just want to mention that we do have an AC voltmeter and frequency meter here. And we have a K-bars button, which is not normally used, but it's telling us when pressed, it allows the kilovolt ampere reactive, the internal losses to magnetizing coils, things such as that, to be reflected on your kW meters for each individual generator. And the residual volts button is used to measure the residual volts for each generator. Now, normally we use that when we press the residual volts button, we're changing the AC voltmeter scale from a 130 volt scale to a 30 volt scale. So naturally we would not want to press that unless our selected generator was not putting out 115 volts. And when is that? When we've disconnected it, among other things, when we've opened the field. In cases such as that, when we've turned the generator off and we just want to see what the internal operation of the generator is doing, then we could measure the field current by pressing residual volts. And we should get something like 10 to 15 volts. It's important not to press that residual volts button unless you have disconnected the output of the generator. In other words, unless the generator is turned off. Otherwise, you might be putting 115 volts on a 30-volt scale. Now, that could ruin the meter, and in fact, it has been said that doing that too often will cause your hair to fall out. Well, that's our discussion of the electrical system. Now let's move down the second officer's panel and talk about the fuel system. Depending on what kind of aircraft you have, the advanced, the stretched, the short bodies, you might have different arrangements of fuel switches here. On the advanced aircraft, they are lined up in a row. Basically, we've got a fuel tank represented by the gauge, and then boost pumps represented by these toggle switches for each boost pump. Now, in the short-bodied aircraft and the stretched aircraft, in fact, all boost pumps are of equal output pressure. On the advanced aircraft, the boost pumps in the number 2 tank, and in fact also in the aft auxiliary tank if one is installed, are high-pressure override boost pumps. Now, the output of the boost pumps can go through the engine fuel shutoff valve to the engine. Or it can go through a cross-feed valve to the fuel cross-feed manifold. And through that method, it could go through another cross-feed valve to any other engine. For example, if we opened up the number 1 cross-feed, if the number 2 boost pumps were inoperative, for example, we could use the boost pumps in the number 1 tank to feed the number 1 engine, and through the cross-feed, provide fuel to the number 2 engine also. That's the best way we have. That's the only way we have, really, other than maladjusting the fuel flows, to balance up unequal fuel tank readings. So we can turn off we can open a cross feed first, establish a flow of high pressure fuel, and then turn off the boost pumps in the tank that we do not want the fuel to burn down in, and we can equalize a fuel imbalance to some degree that way. The engine fuel shutoff switch controls a valve at the trailing edge of the wing tank, at the trailing edge of each tank, which provides fuel to the engine. So we are shutting the fuel off at the tank when we close that switch. Also, pulling a fire handle will close that switch, and on the advanced airplanes, just moving the start lever to the cutoff position will close that switch. The blue valve in transit light means that the cross-feed valve is moving, or that it's not either fully open or fully closed, I should say. The amber lights here are low pressure lights, and they mean that the pump is not putting out pressure. The pump might be operating, but it's got nothing to suck up, nothing in the terms of fuel, or it could be that the pump itself is not operating. So these are really pressure lights. Two important boost pumps that need to be remembered, I would say, are the left forward boost pump and the right aft boost pump in the number 2 tank. And the reason I would say you need to remember those is that they are the 2 boost pumps that are operated off of essential AC power. All boost pumps, by the way, are AC power. So if you were to arrange them in terms of forward and aft on the left tank, forward and aft on the right side of the number 2 tank, we could say it would be Seattle and Miami. The left forward and the right aft boost pump are powered by essential AC power. We're going to look at a basic schematic of the fuel system now. Here's tank 1, tank 2, and tank 3. As you know, tank 1 is in the left wing, tank 2 is in the fuselage, tank 3 is in the right wing. This is a depiction of the engine fuel shutoff valve. This is the fuel that goes to the engine. And this is a depiction of our cross-feed valve. This is the cross-feed manifold. And this is called the fueling and dump manifold. You see, we can fuel the aircraft through here. That's the way we get fuel to the tanks. We come into the fueling and dump manifold, and it goes into the respective tanks. Now, I've shortchanged you a little on the plumbing here to keep our diagram simple, but also we can dump, and we do it through this very same manifold. Whenever we want to take a dump, so to speak, we make sure we have boost pump pressure, because we have to have boost pump pressure to dump fuel. We open up our dump valves which enable that tank to send fuel back to the fueling and dump manifold, and we pressurize the fueling and dump manifold with fuel from each tank. And then we open up our dump nozzles located on each wingtip, and now whatever fuel is pressurized in the fueling and dump manifold will be dumped overboard. So that is another totally unacceptable way of equalizing an imbalance in the fuel. It is not a way of, you cannot use this to equalize an imbalance by, for example, pressurizing the fueling and dump manifold from tank number 3 and then putting it into tank number 1. It won't work. You can't get it to go that way unless you're on the ground. Okay, so that's not a way of balancing the fuel. It'd be nice if you could, but they left the switches off, so that's one of our options that we don't have. Okay, there is some more part of the fueling system, such as the defueling valve and the defueling piping, but I don't think we really need to discuss it in any depth at all to understand the workings of the fuel system. One more time, what will close this valve? Well, moving the guarded toggle switch will close the valve. Pulling the fire handle will close the valve. Or on the advanced airplanes, just moving the engine start lever to the cutoff position will close the engine fuel shutoff valve. And where is that valve located? At the fuel tank. It's not back at the engine. There's a good reason for this. What if an aircraft crashed and you broke the piping that goes from the fuel tank to the engine? You know, those long pipes, because after all, the fuel tanks are up toward the front, the engines are back toward the back. But you were wise enough to pull the fire handle when you crashed. Well, during your emergency evacuation. If this valve were at the tank, which it is, then we don't have fuel going all the way out through that ruptured fuel line, do we? No, we don't. What if the valve were back at the engine, where it used to be? Then what would happen is you'd shut the fuel off going into the engine, but it would still go through that fuel hose, and the fuel hose is now ruptured, so fuel would spill out all over. So that was a good reason for moving it back to the tank, right? Okay. We measure the fuel tank temperature right there in the number 1 tank. In the lower left-hand corner of this picture, we see the fuel tank temperature gauge, and the important thing to remember, besides that the tank temperature is being sensed in the number 1 tank, is that it can't get any lower than minus 36, and if it does, we're going to have to do something about that, like land right away or within a half hour, or go to an altitude where the temperature is a little warmer. The maximum allowable temperature is a plus 49. Now that's a centigrade gauge, and you can see that a plus 49 is pretty darn hot. Could we ever expect to see that in flight? No. How about when we go up to an airplane on the ramp? Well, it would be possible if perhaps we had an airplane that had been sitting in the sun in Las Vegas in the summer all day. In a case like that, we'd have to add some cold fuel or just defuel and add different fuel in, because that is a structural limit of plus 49 degrees, because when the fuel is any hotter than that, the density of the fuel is such that we have a structural imbalance. Right above the fuel tank temperature gauge, we see 3 toggle switches and 3 green lights and 3 orange lights, and that's our fuel heating panel. The orange lights, believe it or not, represent icing. Orange for ice. Well, they're orange lights because, rather amber lights, because we want to get your attention when there's icing. And actually, it's more than just icing. We'll discuss that in a minute. The green light means the fuel heat valve is open. The fuel heat valve, as we can see, is controlled by the toggle switch, one for each respective fuel system. Speaking of icing and freezing, a gal goes into a bar. She goes up to the bartender. She says, I'm new in town. It seems kind of cold out. Is it freezing out there? He says, lady, it's 22 degrees right now, Fahrenheit. She says, well, is that freezing? He says, you idiot, it freezes at 32. She says, well, how should I know? I'm new in town. Let's take a look at the fuel heat system. We've got fuel coming from the engine fuel tank. And this is a picture of our engine-driven fuel pump, the engine-driven fuel pump. We've got two stages of it, stage 1 and, remarkably enough, stage 2. We have a way of bypassing directly stage 1 and just going into stage 2, which could handle all the fuel flow requirements of the engine, by the way. But normally, the fuel goes into stage 1 through a air-to-fluid heat exchanger, which may or may not be operative. This is called our fuel heater. And I say may or may not be operative. If we do not open the airway for the hot bleed air to cross through here, then we don't have any heat exchange taking place, and we just have the fuel proceeding on to the fuel filter. Now, if we decide to use fuel heat, what we are doing is we're taking bleed air, opening the valve, and allowing this hot bleed air to cycle through this air-to-fluid heat exchanger and heat up the fuel. Now, why would we do this? Well, we would do this if we had an icing light, which would be caused by a bypass of the fuel filter. It means the fuel filter is clogged, probably, possibly, we're expecting, with ice crystals. What would happen if the fuel filter was clogged because of contamination? That's right, we'd get an amber light also, wouldn't we? So one of the things we want to check before we just turn on the fuel heat is check the tank of the fuel tank temperature to see if it's cold enough for this to possibly be caused by icing, or if perhaps it's a very warm fuel tank temperature, then we know for sure it's contamination. Okay. We can bypass the fuel filter, and if we do that, we light up the fuel icing light. But if we heat up the fuel, then some of the fuel is going to go through the fuel filter, melt the ice crystals, and then after a while we'll have good flow through the filter, and the fuel icing light will go out. In turn, the fuel goes to stage number 2 of the engine-driven fuel pump. It goes through a fuel control unit here, which I did not draw in, just to keep our diagram kind of simple. And it goes through a fluid-to-fluid heat exchanger, which we call the oil cooler. Now, normally we have hot oil coming in the oil cooler, cold fuel going to the engine, and when the heat exchange process takes place, we have cool oil and slightly heated fuel. That is to say, the cold fuel from the fuel tank and that has been processed by the fuel pump is used to cool the hot engine oil. Well, what happens if we have heated up that fuel? Now we don't have cold fuel coming from the fuel tank and the fuel pump system. We have warm fuel. Well, if it's warm fuel coming through here, the hot oil is not cooled as much. So one of the things we would get, one of the indications we'll get when we use fuel heat is the oil tank temperature goes up. The oil temperature rises. Why? Because it is not being cooled as much from this fluid-to-fluid heat exchanger. What's another indication that we have, that we actually have fuel heat being used? Well, when we open this valve, we'll get a green light. Remember the valve open light. That means the valve is open. What if the valve were open, but there was some kind of blockage or constriction here, and we were not actually getting hot bleed air through the heat exchanger? If we had some kind of blockage that prevented this hot air from getting through the heat exchanger, we would not see any additional load on the engine when we tap off additional bleed air. So one thing we're looking for when we open up that valve is an EP or drop. If the engine pressure ratio gauge shows a drop, it means we have taken off some bleed air from it. So assuming the throttles are up far enough to see an EP or drop, that would be one of our indications. The EP or drop means that air is actually getting through there. The oil tank temperature, or rather the oil temperature gauge showing an increase tells us that in fact the fuel has in fact been heated up. Okay? And is that a problem even if it goes up to the caution range on the oil temperature gauge? No, it's not, because we're allowed up to 15 minutes in that caution range. So that's a discussion of our fuel heat system. Right next to the fuel heat panel, we've got the hydraulic systems just to the right of that. Now we've got two pumps that are engine-driven hydraulic pumps, and we call those the A system pumps. Pump number 1 and pump number 2 on engine numbers 1 and 2. We've got an A system pressure gauge. We've got an A system quantity gauge. And then we've got two electrically driven hydraulic pumps with a lower capacity than the A system pumps. We call those the B system pumps. Electric pump number 1 and number 2. And we've got a pressure gauge and a quantity gauge for the B system. And then we've got a standby hydraulic system. Let's look at a schematic now of what the hydraulic systems power. Okay. If you have that, we don't need to just... Oh, would you like to look at that a little more? Okay. Okay, here we see our A system, and over here's our B system. The A system, as I said, are the engine-driven pumps for engines number 1 and 2. B system are both electrical pumps, AC electrical pumps. The A system provides power to the ground spoilers, the outboard flight spoilers, the trailing edge flaps, landing gear extension, and through the landing gear, the nose gear steering. And it provides power to the ailerons in conjunction with System B, the elevator in conjunction with System B, and through the brake interconnect, we can actually power the brakes from the A system. Also, normal leading edge devices are extended and retracted through the A system, and the lower rudder is powered by the A system. The B system is normally used for the aft air stairs, operation of the inboard flight spoilers, the upper rudder, the ailerons in conjunction with System A, the elevator in conjunction with System A, and the brakes. And we have a device called the ground interconnect, which allows System B to pressurize all of the System A components if it's opened. Now, we can't just open that any old time. There's a switch that we could move. We could physically move the switch any old time, but we have two sets of conditions that must be met for the ground interconnect to actually open up. One condition is, do you recall what those conditions are? Very good, very good. One of the conditions, of course, is APU powering aircraft. And the other condition, these are an either-or type thing, external power plugged in. So we have to have one of those two conditions met. And that's the only two interlocks that we've got for the ground interconnect. But obviously we couldn't meet either of these two conditions in the air. So it's for use on the ground only. And in fact, if we had an aircraft with, say, an A system failure and we wanted to try to taxi the airplane in, the only way we could do that, and I do not recommend this, the only way we could do that would be to actually power the airplane electrical system to the APU. So that means cranking up the APU, power the electrical system with the APU, and then we would be able to do that. We'd be able to use B system to give us, say, nose gear steering. Why is that not a good idea? Well, first of all, the B pumps are a lower volume, lower capacity hydraulic pump system than A. So our nose gear steering would go a lot slower. Secondly, what if we turned a corner, we had low fuel quantity in the number 2 tank and the APU flamed out? Well, we would lose those hydraulic pumps, so we'd lose our nose gear steering, and at the same time, we'd lose our B pumps because we've lost our electrical power, which means we'd lose our brakes. Where are the brakes? Here are the brakes. So I do not recommend that. That's not a good idea, but it would be possible. addition, we've got a standby system which can power both the lower rudder and the leading edge devices for extension but not retraction. And we're going to take a look in just a minute at how that works. So that is the overview of our hydraulic system. Mrs. Olson, would you take this back to the mountains, please? It's the worst coffee I ever tasted. Oh, we're back with you now. Okay, let's talk about the standby system in just a little more detail now. First of all, I do want to discuss how the B tank gets its hydraulic fluid, and that is it's tapped off at about the 2.5 gallon level from the A system. So you could see that any leak anywhere in the hydraulic system, here, anywhere, would not be reflected until the A tank quantity got down to 2.5. It would not be reflected. If it was a B system leak, we would not see it as a loss of B fluid until we had actually depleted the A system down to 2.5. And then we'd notice, after the balance line was depleted, we'd notice the B system quantity going down. So the first indication of a hydraulic leak anywhere is going to be a decrease in the A system quantity, and we don't know where it is, where the leak is, until we get down to 2.5 gallons on the A side, okay? Now, B system reservoir is really divided into two parts. This is a generalization because some aircraft, some models of aircraft, don't have a baffled portion of the B reservoir. They have another miniature reservoir. But we're going to say that all airplanes right now have a baffle here, and we'll just call this little b. Okay, it's a baffled portion. It's not used for operating the B system components. It's just standing by. And in fact, if we developed a hydraulic leak right here, what would we see? We'd see system A quantity go down to 2.5. We'd see system B quantity go down, but we'd still have fluid here, wouldn't we? Sure. And if we developed the leak, here, what would we see? Well, again, system A would go down to 2.5. System B would go down to this level right here, wouldn't it? And then this would be dry. We're not measuring this quantity anywhere on a gauge, but we'd still have B system hydraulic fluid up to here, okay? So that's a discussion of how we tell where the leaks are. The standby system has its own reservoir. This is the standby reservoir, its own separate fluid. We have a standby pump motor, which we can turn on one of two ways that I'll discuss in just a second. If the standby pump motor is turned on, then standby fluid goes to the standby power module and it goes directly to the lower rudder. If we lose system A to the lower rudder, and it is available to this valve right here. Now, how do we get this motor to turn on? There are two ways we get the motor to turn on. Way number one is to turn the A system rudder off. You see, the A system rudder is ganged to the standby rudder switch. So that's the same as saying turn the standby rudder switch on. And when that happens, this motor is turned on. The other way is to position the alternate flat master switch on. And if we take the alternate flat master switch and turn it on, one of the things that happens is this standby pump motor is turned on. We're pressurizing the standby system. Actually, we'll get a little green light on the second officer's panel to tell us the standby system is pressurized, okay? What if we had turned on the alternate flat master switch, thus turning on the standby pump motor, and then later we lose A system to the lower rudder? Well, then in that case, we would automatically get the standby actuator to the lower rudder powered through the standby system. But as long as we have A system powered to the lower rudder, we will not get that in effect. We'll talk about that a little later when we talk about flight controls. For now, let's talk about that valve. You know, if we open that valve, we will be driving a hydraulic motor with standby fluid. And that in turn is ganged to a hydraulic pump which draws fluid from little b and sends it out to the leading edges for extension. Extension only, not retraction. Now, why do we have this motor and pump assembly? It's so that we have a total isolation. We are not sending standby fluid, that's this fluid here, out to the leading edge devices. We are only sending little b fluid out to the leading edge devices. And that's important. We've achieved isolation this way. And so even if we had a leak in the leading edges, for example, the most fluid we could lose would be the entire little b reservoir, the baffled portion, but we would still have standby system fluid to go to the lower rudder. So that's important. Now, how do we open this? We position either of the two alternate flap electrical switches, the inboard or the outboard, to the down position. And by momentarily moving either of those electrical switches to the down position, we have irrevocably opened that valve. It's going to stay open, and now we are immediately extending all of the leading edge devices fully. All right? So that's a discussion of our standby system, the plumbing involved in the A, B, and standby systems. You'll notice here we've got an overheat light for the A system, an overheat light for the B system, and in fact an overheat light for the standby system. The A system fluid is cooled in the number 3 fuel tank. The B system fluid is cooled in the number 1 fuel tank. We've got fluid-to-fluid heat exchangers. The standby system fluid is not cooled anywhere. Now, if we've got an overheat, depending on the model of airplane we've got, it could be sensed in the return line, it could in the module itself. It could be an overheat sensed at the pump outlet. So we're just going to have to follow the book procedure depending on the specific airline irregular or emergency procedure. But basically what we're going to be doing is turning one or both pumps off, wait till the overheat subsides, and then turn the pumps back on one at a time and see if we can find out which pump or which pump is causing the overheat. On most airplanes there is no accumulator in the A side, and on the advanced airplanes there is no accumulator on the B side, but on the non-advanced airplanes there is a 2,000 psi precharge on an accumulator. So a loss of B system pressure, if you had an accumulator, would be reflected by the pressure gauge falling to accumulator precharge pressure. The hydraulic brake interconnect valve, and that's one that we talked about before as being a way of getting the A system to pressurize your brakes, is directly above your B system switches. It's a guarded switch, and when you open that, you'll get a green light. That means the valve is open. It's directly next to your brake pressure and quantity gauges. Your pneumatic brake correction and your hydraulic brake pressure gauges. Now, when would you use the hydraulic brake interconnect? Would you use that if you've got a brake leak and you've lost your entire B system fluid? No, you wouldn't, because in that case, if you opened that up, you'd be pumping A system fluid out the same brake leak. You'd end up losing A system fluid also. So you would really only use that if you lost your B pumps. Let's say you had either a pump failure or an electrical failure for both pumps. In that case, let's say you had an overheat on one pump and then a pump failure on the other, or some such instance, or a complete electrical failure. In that case, you could get brake pressure by opening the hydraulic brake interconnect valve and getting A system pressure to the brakes. Not to be confused with your ground interconnect valve, because we decided already that that's to allow B system to pressurize A system components, and once again there's only two things that will allow us to open that up. One is external power plugged into the airplane, the other is APU powering the airplane. By the way, can you think of two other instances that work the same way as that? Two other conditions that must be satisfied, one or the other, to make something happen, where we have APU powering the airplane or external power plugged in. Very good. We're getting a little ahead of ourselves, but that's absolutely right. The amber lights on the stall warning system directly over the captain's head come on when external power is plugged into the airplane or when APU is powering the airplane. So I like to think of those amber lights right there as being my indication that we have a hot ground interconnect switch. The ground interconnect switch is enabled whenever those two amber lights are on. It's the same set of conditions for both. Now let's take a break and get back to that coffee. Now let's move up the second officer's panel, and the next gauges we come across we don't really need to discuss in any detail. They discuss the oil. We have an oil pressure gauge, an AC operated gauge. We've got an oil temperature gauge, and remember the yellow band, the caution band, it's okay to be in that for a little while, and in fact you would see the temperature edge up toward there when you use the fuel heat. The oil quantity gauge. We've already talked about the electrical volts and ammeter for the DC system. We have three lights here called strut or lower aft body overheat lights. Now, there are very complicated procedures relative to what you do if these lights come on, but basically these detect a bleed air leak. So if we have a bleed air pressure leak, this light will, one of these lights will come on. If it's a bleed air leak in the strut, we get the strut light on. If it's a bleed air light in the, if it's a bleed air leak in the lower aft body, which is anywhere along the keel beam, over the aft cargo pit, along the aft air stairs, anywhere of numerous places, we'll get a lower aft body overheat light on. Those of you used to flying the non-advanced airplanes might notice that we've got a light missing. On the advanced airplane, we do not have a wing anti-ice auto trip-off light. It's not installed, and the reason it's not installed is that the electronic pressurization controller is so good at accommodating for pressure surges that we don't need the wing anti-ice auto trip-off system. The lights for the bleed air leak will indicate the same as they would on the short body, and so we can solve any problem, any bleed air problem, with these three lights and the appropriate checklists. If we have a wing anti-ice auto trip-off light or the wing anti-ice auto trip-off system installed, it will sense a rapid decrease in cabin pressure, that is, the cabin pressure falling. We'll note that on the cabin rate of climb will be pegged off scale in the low direction. If the cabin is rapidly falling, this means we've got a bleed air leak somewhere in the ducting that goes to the wing anti-ice system as it passes through the cabin, through the pressurized hull of the aircraft. And if we have a leak in that case, we're pumping air that was intended for the wings into the pressurized hull, and that, of course, pumping additional air into the pressurized compartment will cause the cabin to descend. If the cabin is descending at an excessive rate for a couple seconds, then the wing anti-ice auto trip-off light will illuminate, and in addition we'd probably have a lower aft body light illuminated also, because that tells us we've got a bleed air leak somewhere, probably along the keel beam, as the wing anti-ice ducting goes from the engines all the way up toward the wings. And then the wing anti-ice valves will be closed automatically so that we don't have to worry about continuing to pump that hot, high-pressure air into the pressurized hull. We'll discuss some of the sensors in the wing anti-ice system, but for now, let's just call this a rough overview of the wing anti-icing system. This is engine number 1, provides anti-icing, and engine number 3 does the same. Okay, and like I said, when we talk about the anti-icing system, in about an hour, we'll discuss this in greater detail. Engines number 1 and number 3, through wing anti-icing valves right here, provide air up a common duct, and it branches out to the two wings. Now let's say that this is the pressurized part of the airplane, because obviously air has to get all the way from the tail where the engines are up to the front of the airplane where the wings are, okay? So this piping goes through the pressurized hull of the aircraft, and we'll pretend that we have just developed a leak right there. Well, you can see that if we're pumping air into the pressurized hull, that is increasing the cabin pressure, which means that the cabin altitude is going down, right? Okay, we're over-pressurizing the cabin. So what will happen will be the wing anti-ice auto trip-off system will automatically close these two valves so that we are no longer pumping air into the cabin. In addition to that light that we get saying, hey, we're over-pressurizing the cabin, we'll probably get a lower F body overheat light because the hot bleed air is probably spilling on one of the overheat detectors along the keel beam. So we would actually see two lights. We would see the lower F body overheat light. Then, after a short period of time, we would see the wing anti-ice auto trip-off light, which means that the system has responded and these two valves are closed now. And then after a short time, again, when the detector over here has cooled down sufficiently, the lower F body overheat light will go out. Now, what would you expect to be the very next thing that would happen if the wing anti-ice auto trip-off system has worked properly? That's right. We are no longer pumping air into the cabin. The cabin is no longer descending. But what about this hole here? That is allowing cabin air now to escape via the wing anti-icing system, because there's no way to shut off an outflow of air through the wing anti-icing system along the wings. So we're going to get cabin air going through this hole, and that's virtually the same as developing a leak in the pressurized hull. So the cabin now will climb. How much will it climb? Well, that depends on the size of the leak here. I told you that with the electronic controller, they feel that that can shut the outflow valve quickly enough so that we don't even need to worry about the cabin climbing very much. If this was a very, very large hole, well then, even if the outflow valve or valves were shut completely, we may not be able to stop all the outflow of cabin air. So that will depend on how big a hole we've blown here. And once again, that would be a light that we would see right here if we have the wing anti-ice auto trip-off system installed. What we would see one more time is a lower F body overheat light, followed by a very noticeable sensation in our ears as the cabin descends, followed by the wing anti-ice auto trip-off light illuminating. Shortly after that, the lower F body overheat will go off, and the cabin will go from a descent to a climb, and hopefully it will then stabilize when the pressurization system takes over and gets control. The aft cabin zone controller we'll talk about later. It's only installed on long-body aircraft. Right above it, we've got the auto-pack trip system. The auto-pack trip system is only on the long-bodied aircraft, and the purpose of the auto-pack trip system is in the event of an engine failure or a loss of thrust on takeoff, if the system is armed, it will turn off both air conditioners. Now what that will do for you is it will download you pneumatically so that all of the thrust available is going toward, all of the engine output available is going toward thrust. And it will electrically download you because we won't have the pack fans running. So if we've lost an engine, that means we're down to at most 2 generators. We won't have any excessive loads from the pack cooling fans because, as we're going to discuss in a minute, the air conditioning cooling fans are a very high load electrical item. How do we get that to work? Well, we need several things to arm the auto-pack trip system. We need to be on the ground sensing. We need to have the flaps, the inboard trailing edge flaps, not up. So they have to be somewhere out of the up position. We need to have all 3 engine pressure ratio gauges above 1.5. And we need to have this switch in the normal, as opposed to cutout, position. So those are the 4 conditions we need to arm the auto-pack trip system. And then, if it is armed, if we have a loss of thrust in any engine below some threshold, and it's about 1.5 EPR, but the number is unimportant. If we have a loss of thrust below some threshold, then we will get 2 trip-off lights on our air conditioner packs. Both packs will turn off, the fans will stop, and in addition we'll get engine failure lights on each glare shield. One on the glare shield for the 2 guys who sit up front. One on the left and one on the right, engine failure lights to instantly tell you of a power loss. So that's a good deal. And in fact, you can dispatch with a higher weight when you have an auto-pack trip system than if you didn't. Why? Because you have instant recognition of engine failure. And you have instant electrical and pneumatic downloading in case you do have engine failure. So actually you could take off with a higher climb limit gross weight and a higher runway limit gross weight. How do you disarm the auto-pack trip system? 2 ways. You can take the switch and position it to cut out. That will disarm it. Or you could raise the flaps. That will disarm it. Now here's a hypothetical example now. Let's say that we take off, we forget to put the switch to cut out, we being the second officer, forget to put the switch to cut out. The green light is still on whenever the system is armed. We don't notice the green light, and after a while we raise the flaps after takeoff and the green light goes out. Why does the green light go out? Because the green light says auto-pack trip armed, and the green light is no longer, the auto-pack trip system is no longer armed. When is the next time that the system will rearm itself? No, it will not rearm itself when we lower the flaps prior to landing. Why? Because we don't have on-the-ground sensing. Okay? The next time it will rearm itself, that's right, is when we're doing our reversing on landing. Sure, we have on-the-ground sensing, we have flaps extended, we have all 3 EPRs above 1.5 probably, and the switch is still in the normal position because we forgot to put it to cutout. So during reversing we'll see the green light come on, and unless we're very, very quick to disarm it, which we probably won't be, as soon as we come out of reverse, when the EPR drops below some threshold, about 1.5, both packs will trip off. Very embarrassing. That's the auto-pack trip system. Okay, just above the auto-pack trip is an oxygen pressure gauge. It's for the passenger oxygen only. And it tells you the pressure for the oxygen system for the passengers. And actually there are 3 ways to pressurize the oxygen system for the passengers, to pressurize the manifold to the masks. One is with this toggle switch here. You take it from normal and go to on, so you're electrically toggling it. And in that case, when the system is pressurized, we'll get an amber light. It says on. It just means the manifold to the passenger oxygen masks is pressurized. Another way is to pull your manual handle, which could be located in any one of a number of places below the floorboards, just in the center aisle aft of the door, or it might be on the second officer's auxiliary panel. Depends on the model of the airplane. And the third way is for the cabin pressure to go up to 14,000 feet. Okay? If the cabin pressure goes up to 14,000 feet, we automatically deploy the masks. That is to say, we automatically pressurize the manifold, and that air pressure deploys the masks. You know, a very interesting thing happened the other day when I went out to pre-flight the airplane. I was walking around the exterior, and the guy was, the blue room man was just trying to button up the forward lavatory servicing, and the valve came loose, and the entire holding tank from the forward blue room on the right side spilled all over him. Oh, what a mess. And I was looking at him and just kind of feeling sorry for him when I recognized him as one of our second officers who was furloughed, recently furloughed. And I went up to him and I said, hey Joe, I thought you had a PhD in electrical engineering, didn't you? He says, yeah, I do. I said, well, Why didn't you get yourself a job probably for 4 times this pay as an electrical engineer somewhere? Why are you cleaning toilets on 727s? Why don't you get yourself a good job? He says, what? And leave aviation? Now we're going to talk about the air conditioning and pressurization system. The upper right panel on the second officer's station. The first thing I want to point out about this is, schematically, it is not correct. That is to say, it would have been much better had they taken the sub-panel here for heating and air conditioning and placed it right above the pressurization panel, and then we would have a schematic representation of air coming from the engine to the air conditioning pack, to the air mix valve, and then on to the cabin or the cockpit. Unfortunately, they didn't do that way, and so we're going to talk first about the pressurization system, and next we'll talk about heating and air conditioning. Although they are related, as you know, because what we are doing is we're putting either heated or cooled air into the cabin and cockpit, and by modulating the outflow of that air, we're maintaining pressurization. What we've got is air coming from engine number 1 through a bleed air switch, the engine bleed, and then it goes to a pack switch, which controls air to the air conditioner pack. And then that air goes from the left pack predominantly to the cockpit, from the right pack, which is mostly fed by the right number 3 engine, goes to the passenger cabin. And we have the capability of taking air from the number 2 engine to either one of those packs through the number 2 air bleeds. This is a schematic representation of the right pack powered by the number 3 engine, although, as I said, it could get its air from the number 2 engine also. Air comes in through the pack valve, and then some of the air can go, this is hot air, remember, this is hot bleed air from the 8th and 13th stages of the engine. Air comes up, and now some of that air, the air that we want to be hot, the hot air that we're going to use, goes directly up to the hot air mix valve. But some of the air that we want to cool, goes through 2 heat exchangers, which we call the air cycle machine. It is made cold, and then it goes to the cold side of the air mix valve. Okay? So first it goes through a primary heat exchanger, where we take ram air and pass it over a heat exchanger to cool this hot air, so now it's just warm. And here it was hot when it came in, and now it's just warm. It goes through a compressor, and then it goes through a second heat exchanger, so we call this the secondary heat exchanger. And then it goes through an expansion turbine, where it's cooled off even more. And so when it gets to the air mix valve, it's very cold air. Now this turbine and the compressor are ganged together, hooked together. And so as long as we have air coming in, the machine's working. And it works pretty well. We've got some subsystems in here that might be worth talking about. One is, well, what happens if there's moisture in the air and we've cooled the air down below 32 degrees? Well, then the moisture is going to become ice. And so what we do is we take some hot air and we send it to a thing we call the water separator, and it's just a little bit of hot air, a small line of hot air, and the whole purpose of that is to melt the ice. So we see water on a hot day, a day when there's a lot of moisture in the air, because as you know, hot air can hold more moisture than cold air, so it's mostly seen on hot days. You'll see a lot of water dripping from the water separator. The cold and the hot air mix valves are ganged together. So in this case, we see the air mix valve arrangement so that nothing but cold air is coming in, the hot air is cut off, okay? And they're ganged together so that now we've got one manifold that the air is coming into. We could select any number of intermediate positions all the way to the other extreme, and that is no cold air and nothing but hot air. And in that case, of course, no air would go through the air cycle machine. The more workload we put on the air cycle machine, the hotter it gets. Now that stands to reason. So what I'm saying really is that if we ask for a lot of cold air, we could expect this air cycle machine to warm up, to heat up. And if the thermal load on the air cycle machine is too great, if we see it overheating, what could we do to reduce that thermal load? That's right. We could request less and less cold air, and that would put less of a workload on the air cycle machine. Okay? Well, you know, there are several ways to get a pack to trip off. And basically, a pack will trip off, that is, it will turn itself off through protective circuitry and illuminate the pack trip-off light. The reason that would happen would be because of an overheat. Okay? There are 3 types of overheat that will cause the pack to trip off, and we're going to discuss 2 of them right now, and then when we talk about the next subsystem, the air conditioning system, that is the temperature regulatory system, we'll talk about the 3rd. Right here, at the compressor outlet, we have a temperature sensor. In fact, we have 2 temperature sensors, okay? One temperature sensor goes to a temperature gauge. Okay? The other temperature sensor goes to the trip-off circuitry. Okay? They're sensed at the same place, at the compressor outlet. So if the temperature here is getting warm, we will know it by looking at the temperature gauge, the pack temperature gauge. And if it gets too warm, and that point is the red line on the temperature gauge, and the number is unimportant, when it gets that warm, then the protective circuitry comes in and it will trip the pack off. It says, okay, I gave you your chance, second officer, to do something about it, and you didn't, so now it's my turn, I'm turning the pack off. Okay? So, they are both taken at the same place. There is one other place in this schematic that we have a protective trip circuitry, and that is right here at the turbine inlet. We also have a trip protective circuitry, but we don't have a temperature gauge there. So the first time we'll know that the temperature is too hot at the turbine inlet is when? That's right, when we see a trip-off light illuminated. Now here's a question for you. Let's say that we're flying along. Just as we look up at the air conditioning panel, we see the trip light illuminate, the air conditioning pack trip-off light illuminate. And we look at our temperature gauge real quick, and it's right around the middle, right around 100 degrees or so. What does that mean was the problem? It was not a trip from the compressor outlet, or we'd have seen it as a red line on the temperature gauge, right? So it must be a turbine inlet trip, because that is not a temperature we can measure anywhere. Okay, I talked about the primary and the secondary heat exchangers. How do they get cooling air? Well, the cooling air is regulated by what we call the ram air cooling doors, sometimes referred to as the alligator doors, in the belly of the aircraft, and they can go from full open to full closed. Total movement, maybe 1.5 inches or 2 inches. So it's not a very large movement, but they are very efficient and effective at controlling cooling. Okay? They are, okay, I'm going to show just a small movement here. Why else are they so efficient? Because they are mechanically linked to exit louvers behind the primary heat exchanger. And so maybe the front ram air door does not close all the way, but these louvers go very close to closing all the way, and if we control the outflow of air, then regardless of how much air we have enabled to come in, we're not going to have any flow of air through here if we don't let it come out somewhere. So you got to look at this as an entire system, and that is we have the ram air cooling doors mechanically linked to the exit louvers, and that is what controls the flow of air very efficiently across the heat exchangers. Okay, and once again, these are the cooling doors in the underside of the aircraft fuselage. Now we have another way of getting cooling air across here, because let's face it, what if we're on the ground operating the air conditioner? We're on the ground and we're not moving, and we're operating the air conditioner. How do we keep the thing from heating up, and how do we keep cooling air across the heat exchangers to get a good heat exchange process? Sure, we have a pack fan, and that's what I was referring to before. The air conditioning pack fan, one for each air conditioner, and we'll draw it right here. That fan is running anytime the airplane is on the ground and anytime the flaps are extended. So if we're in the air with the flaps extended, that fan is running. You notice I drew a one-way check valve here. Now what that amounts to is a swinging door, kind of like what you find at your favorite drinking establishment. Can only swing one way, open. Okay? Can only swing open. And we've got a similar type door right here, by the way, a swinging door. And this is a motor-driven swinging door. This is an air-controlled swinging door. If we have airflow through here, it will open. If we don't, it'll just stay shut. This swinging door is motor-driven open whenever the fan is turned on. Now I want to discuss just very hypothetically with you something. What if we're here at ground speed 0 on the ramp? We're just sitting on the ramp. The air conditioner is turned on. Therefore, since we're on the ground, this fan is running. What will be the position of this door? That's right, it will be closed. And why? Because we've got air coming in here, and some of that air is coming here and pressing against that swinging door to keep it closed. Okay? We've got air pressure actually holding that door closed. What would happen if we're taxiing now on the ground through a lot of slush and ice? And let's say we had left this ram air cooling door in the full open position, and ice is being thrown up from the nose wheel and just by virtue from blowing snow and so forth, and ice is building up here. Well, sure, we're going to get a whole wall of ice here because this door is being held shut by air pressure. Okay? If we had to pack off, if this fan was not operating, any slush or ice that was thrown up here would probably be enough pressure to get the swinging door to open, and so we'd get the ice building up on the heat exchanger rather than on the door inlet. Now, every airline has a different procedure, but I just want to put that in your mind so that you understand the slush procedure for your own airline, because chances are it revolves around something like this, making sure that at least one of our air conditioning packs stays operative and stays uniced by leaving that pack off during ground operation in slush or ice. On the advanced airplane, we have 3 air mix valves instead of 2. We've got an air mix valve for nothing but hot air, just like here. We've got an air mix valve for nothing but cold air, just like here. And we've got another air mix valve for air that has gone through the heat exchangers only. Has not gone through the air cycle machine, that is the compressor and the turbine, but has actually gone through the heat exchangers. So we have a 3rd air mix valve that we'll call lukewarm or cool air. And so the operating temperature for the air conditioner pack for the stretched and advanced airplane, the optimum operating temperature is a little different than the optimum operating temperature for airplanes, the short bodies, those that have only 2 air mix valves. Just one other thing I'd like to discuss, and our drawing is getting a little clumsy now, but that is the ram air valve, because some airplanes have a ram air switch, and what that does is it allows ram air, which would come in through our ram air doors, to go into the cold side of the air mix valve. You would only use that when the pack is turned off. If you wanted to try to get some kind of ram air pressurization. So here the pack is turned off. What position do the air mix valves go in when the pack is turned off? That's right, they go to the full cold position. And that's one reason, so that any ram air that comes in here would be able to go into the ducting for pressurization. Not all airplanes have a ram air switch, but if they do, it is getting ram air from this ram air doors and cooling mechanism here, primary and secondary cooling coil system, into the cold side of the air mix valve. Now we've gotten the air through the air mix valve, and now let's talk about what happens after that. We've got a valve position indicator for the left pack and for the right pack. The left pack is called control cabin, that means cockpit. The right pack is called passenger cabin, that's the cabin. And they are predominantly used for that purpose, although as we'll see in just a minute, you could get air from either pack to go to either place. We've got an automatic temperature rheostat with which we select the temperature we desire for the left pack and for the right pack. That is, we select the temperature we want in the cockpit and the temperature we want in the cabin, and that talks to the air mix valve through a feedback system to tell the air mix valve where to go, either full cold, full hot, or some point in between. We've got a duct temperature gauge, the only Fahrenheit gauge in the whole airplane, and it will tell you either the supply duct temperature, the cabin temperature. We've got 5 positions that we can read from on this wafer switch on the long-bodied airplanes. The short-body just have 2, cabin or supply. But on the long-body we've got forward and aft cabin, main supply, forward and aft supply. Here we see our left pack, the air mix valve, the ganged cold and hot valves, and the right pack, the cold and hot valves for the right pack, okay? The output of these valves, the output of the packs, goes into a common manifold, but predominantly, that is to say physically located near those valves, is the tap-off for the cockpit or the cabin, okay? So that's why we say the left pack goes to the cockpit, the right pack goes to the cabin. Obviously, if we only had one pack working, the air from this pack, in addition to going to the cockpit, would also go to the cabin. Now, we can modulate the air that goes to the cabin to either the sidewall or the overhead or some intermediate position of those. Overhead ventilation results in a noisier cockpit ventilation, and it results in a faster change of temperature. So if we need to cool the cabin off or heat the cabin up very, very quickly, overhead is the position to do it. But it does create a lot of airflow noise. Sidewall, on the other hand, just, is a lot quieter, but it's not quite as effective and, well, I'll say efficient, in that it will not as quickly change the cabin temperature. We've got some protective circuitry now. On each side, we've got a 140-degree temperature switch. We've got a 190-degree temperature switch on each side. And in addition, we've got a cabin temperature, a duct temperature gauge pickup. So this goes to the gauge itself. We can only monitor the duct temperature on the right side of the system. That is, when we go to supply duct, we are only measuring the temperature on the right side, the passenger side. However, we do have protective circuitry on both the left and the right side. What is the 140? Well, the 140 is what we call the topping circuit. If we get so that the duct temperature exceeds 140 degrees, even though we can't read it on this side, we can only read that duct temperature on this side. But on either side, if the duct temperature exceeds 140 degrees and we are in the automatic position, then the air mix valve will not move any further toward hot. It doesn't make the air mix valve move toward cold. It just means the air mix valve will not move any further toward hot. When we reach 190 degrees on either side, then we get the duct overheat light illuminated. Okay? 190 degrees will illuminate the duct overheat light. And then if we reach off scale high, I'll call it 250 plus or minus something, off scale high on the duct temperature gauge, and it's about 250 degrees, the pack will trip. And that was the third way that we were talking about of a pack tripping. Okay? Now when would that happen? Well, let's talk about that. At 190 degrees duct temperature, whether we're in automatic or manual, at 190 degrees this duct overheat light will illuminate. And one of the things that the duct overheat light does, the duct overheat system does, is it will drive the air mix valve to full cold. So why would we ever get 250 degrees? Obviously there's been a malfunction somewhere. Either this switch did not function properly, or maybe the air mix valve physically stuck. Maybe it's a motor-driven valve. Maybe the motor on the air mix valve burned up. And now we've got ourselves with a stuck air mix valve in the full hot position, perhaps. Okay, this is our way of avoiding getting smoked out of the cockpit, burned out, and that is trip the pack off. So if worse comes to worse, if you've exceeded 190, the duct overheat light either hasn't come on because this switch malfunctioned, or the duct overheat light came on but the air mix valve never went to cold, you couldn't control it yourself, then the pack is tripped off. So that's your own personal protection, that you're not going to have a pack run away to the full hot position, overheat everything, start burning out all the plastic molding and everything in the airplane and not be able to control it. Now you would smell some burning fiberglass and insulation and things such as that from the excessive heat long before that thing tripped. And you'd know there's something seriously wrong. Okay, the 140-degree topping circuit only works in the automatic position. So if you're in manual, you're not going to have that protection. And is it really that much protection? Well, let's take a hypothetical example. Let's say I'm in the automatic position. I select 70 degrees. I have gotten into an airplane that's sitting on the ramp at Chicago in the middle of the winter at night. The temperature inside that airplane now is, and inside the ducting, is, we'll say, 0 degrees Fahrenheit. Okay? Because is that a Fahrenheit or a centigrade temperature? Right, it's Fahrenheit, okay? I turn on the pack and I have asked for 70-degree temperature. What will the air mix valve do? Sure, it will go as fast as it can toward full hot because it is continuously sampling the temperature of the air in the ducting and in the cabin. And it is saying, okay, right now the air is 0 degrees, I need to go hot. 3 seconds later it's saying, okay, the air is up to 1 degree, but I still need to come further hot. So you can see that long before the temperature in this duct reached 140 degrees, the air mix valve would have fully opened up all the way. So has that protective circuitry really helped us much? No, it hasn't. Okay? So in a case like that, what I would suggest personally is that you go to the manual position, manually move the air mix valve to around the middle position, the 12 o'clock position, then monitor the stabilized duct temperature. And that's one good reason to use the right pack, because it's only the right side where we can monitor that temperature. So we have an automatic system, and if we wanted to go to manual, then all we would do would be position the rheostat to the bottom or manual position, and in that case, the air mix valve never moves until we tell it to move. We have to physically toggle it. It's spring-loaded to the center or off position. We have to physically toggle it toward cool or toward warm to get the air mix valve to move. And once again, when the pack is turned off, where is the air mix valve? That's right, it goes to full cold. Okay. This is the air conditioning, or rather the pressurization monitor panel. We've got a cabin rate of climb to tell us how fast the cabin is climbing. And then we've got a two-part gauge, one that shows the differential pressure in pounds per square inch, and the other part of the same gauge shows the cabin altitude. Now on the electronic controller, we've got a little dial below that, or rather a little strip that shows us what the cabin should be for any particular cruise altitude. That is to say, and you can look at your fold-out along with me here, if we wanted a cabin altitude of 32,000 feet, rather an aircraft altitude of 32,000 feet, we'd want the cabin at 4,400 feet. Okay, and if we wanted the airplane at 40,000 feet, well, that would tell us a couple things. It would tell us that the captain did not choose the correct hemispheric cruising altitude, but in addition, it would tell us that we wanted a cabin altitude of 7,300 feet. Over here, we've got the electronic pressurization controller. Probably the best thing since sliced bread as far as controlling the cabin pressure on a 727. You see, on the older short-bodied airplanes, we have a pneumatic pressurization controller. It uses nothing but air to control the position of the outflow valves. If you have enough air present, then you can effectively control the position of the outflow valves, 2 of them, unless they happen to be gummed up with nicotine from having had a lot of smokers on board over the years, and nobody's cleaned them for a while. But with this system, we've got one outflow valve, electrically controlled. It's a sliding gate type valve, and so it is not as subject to sticking as the pneumatic outflow valves are. Okay, we've got several positions on this electronic controller. First, let's discuss the lights. We've got an auto fail light, an off schedule descent light, a standby light, and a manual light. Okay? The auto fail, that light will illuminate and the system will automatically go into the standby mode under several circumstances. If we have an excessive interruption of electrical power, by that I mean a couple seconds worth of interruption of electrical power, the system will auto fail and go to the standby mode. If the cabin exceeds 14,000 feet, the system will auto fail and go to the standby mode. If we have an excessive rate of cabin climb or an excessive rate of cabin descent. Now those are all times when this thing is not doing its job. So we want it to go to the standby mode. We don't want it to stay in the automatic mode. So that's a good deal. Okay? What does the standby mode do? The same thing the normal mode in the old type system does. Okay? We've got a standby controller in the very center of our electronic controller that works virtually the same way, except it uses an electrical outflow valve instead of pneumatic. Works just like the old type pressurization system controller. Let's start in the upper left-hand corner now of the control panel itself, forgetting about the lights for a minute. You notice in the left-hand side at the top, we've got a flight altitude window for the automatic controller. We dial in the altitude we desire to go to. Just below that is another window for your landing altitude. Now, if everything works great, and we're going to say 35,000 feet, and we're going to land at, say, Denver with an altitude of 5,300 feet roughly, we set in 35,000 in the upper window as you see, we set in 5,300 in the lower window as you see, and just prior to taking off we move the ground flight switch from ground as it is now in the lower center to flight. The airplane will pressurize itself, it will maintain the proper pressurization schedule as we climb up. When we depart 35,000 feet, it will start the cabin back down to 5,300. Assuming we never reached 35,000 feet, but we had to, halfway through our climb, we had to return to our takeoff base, then we will get an off-schedule descent light, but the cabin itself will go back to whatever cabin altitude we were at when we took off. Actually, it'll go to 200 feet below that. So if everything works right, we don't have to touch that system ever again. We go up to 35,000 feet, the cabin goes to whatever it's supposed to go to. In this case, actually, at 35,000 feet, the cabin will go to 5,600 feet. When we land, the cabin is back to 5,333, or 200 feet below that in actuality. If we never got up to our cruise altitude, then the pressurization system assumes that we have aborted our mission, and as soon as we start a descent, it will bring the cabin to 200 feet below whatever our takeoff elevation was. What if we had been assigned a new altitude of, say, 31,000 feet instead of 35,000 feet? If we do not reset the flight altitude, then when we start our descent for Denver, we will get an off-schedule descent light, which means the system thinks that we are rejecting the mission and going back to our takeoff base. How do we get rid of that? We just dial in a current flight altitude, whatever our current flight altitude is, in the flight altitude window, so that as far as the system is concerned, we made it up to our cruise altitude. Okay? That's it. How about the standby system shown in the center? Well, the standby system, as I said, works very much like the normal automatic system in the short-bodied airplanes. We set in a cabin altitude that we desire, in this case 5,400 feet. Right above that is the rate knob, and we set in a rate anywhere from 50 to 2,000 feet a minute that we want the cabin to try to go to that altitude at. And if we set it opposite the little triangle, it'll give us about 300 feet a minute of cabin movement. If we're halfway through our climb in the automatic mode and we get an auto fail, it goes to standby, what will happen? Well, the cabin will try to go to 5,400 feet. At what rate? In this case, 300 feet per minute, or whatever rate we have set with our cabin rate knob. Full counterclockwise is full decrease, or 50 feet a minute, and so forth. Once again, the ground flight switch will tell the cabin to start pressurizing to whatever we've selected. And then once we're airborne, just as in the automatic mode, the ground flight switch has no effect because the airplane knows it's in the air. Now on the far right, you can see the manual controller. Now one would get the impression from looking at that as though the outflow valve position indicator only works in the manual position, and that's not true. That valve position indicator shows you the amount of openness or closeness of the single sliding outflow valve in all three control positions of our air conditioning pressurization control system. Okay? Now we can, in the manual position, move that outflow valve either fast or slow, incrementally or continuously. How do we do that? First, you can go to manual AC or DC on the lower right selector switch. Manual AC will move the valve faster than manual DC. So we've got two different kinds of motors that drive that outflow valve, either an AC motor or a DC motor. Taking the flight ground switch to flight will give us incremental movement, and that's because we don't want the outflow valve to move a whole lot at one time when we're in flight, because just a little bit will greatly change the cabin altitude. But if we're on the ground, we can go to ground position and move it continuously. And in fact, if we're in the air, we can go to ground position and move it continuously if it's some kind of pressurization emergency. Moving the center right toggle switch to the left will close the valve. Moving it to the right will open it. And if we had a runaway cabin pressurization, a cabin pressure leak of some kind, where we were losing cabin pressure, we could go to ground and move the spring-loaded toggle switch to close to the left, or in effect squeeze those two toggle switches toward each other. We would have continuous movement of the outflow valve toward closed, and that should control the cabin pressure. Now in the lower right part of the second officer's panel, we've got a cluster of three lights. The first one is labeled no equipment cooling, and what that means is there's a sensor that senses actual airflow out of the lower equipment bay, and when it does not sense enough or any airflow, this light will illuminate. Now that doesn't mean your equipment's already gotten hot, but it's going to get hot pretty darn quick. So you got to do something about that, and there are book procedures as to what you should do. In effect, we've got several ways of controlling the outflow of air from the lower electronics bay. One is to raise the cabin altitude so we have a greater differential of pressure. The other is to lower the cabin altitude so that we have more exit holes open. But that will be up to your specific airline procedure. The next light over is called elevator field differential pressure light. And it's worth discussing what that light tells us. As you know, with the T-tail airplane, we've got to worry about things called deep stalls, and we want to make sure that we give ourselves further protection from a stall than perhaps we would use with other types of flight control systems. Now, we're going to talk about flight controls later, but for right now, I just want to remind you that we do have both A and B system going to the elevator, and we've got a thing called an elevator field computer, which gives us artificial feel so that we do not over-control the aircraft. Okay? Now, what does the computer do? It takes the input, either System A hydraulic or System B hydraulic, and modulates the feel, which then allows us to control how much input we give to either the A system elevator or the B system elevator. How does it modulate that feel? Well, it takes our airspeed as sensed by the pitot input for the A side, the pitot input for the B side, and it determines how much feel we should have. What if there's a significant difference between the output on the A side and the output on the B side? Well, there is a comparator, and when there's a significant difference, this comparator lights up a light. That is the light on the lower right-hand corner of the second officer's panel. It says elevator field differential pressure. It means there's a difference in pressure. Now, would we expect to see that light illuminated if we've lost one of our hydraulic systems? Of course. If we've lost the B system, we do not have any B system pressure going to the elevator. We only have A system pressure, and we would expect this comparator to say, hey, I got A system pressure and no B. So the light lights up. Is it a problem? No, it's not a problem. But what if we have operative, good A and B systems, and this light illuminates? Well, then we have a problem. We could pull back on the stick with 3 ounces and get 8 Gs. What might the problem be? Well, the problem might be, and this might not be in your book, the problem might be a blocked pitot tube. So one of the things that I would check if I saw an elevator field differential pressure light is pitot, the A and B system, or the left and right vertical stabilizer, pitot amperage, to see if the pitot tube is drawing current. Because what if this one is not drawing current? Then it means that perhaps all we need to do is reset the circuit breaker. In fact, some airline procedures for an elevator field differential pressure light merely say, fly the airplane normally and avoid abrupt control inputs. All 727 pilots fly that way. The lower rudder load limiter is one of the more confusing subsystems on the 727. So let's talk about that for a minute. Let's envision this as a continuum of different values of hydraulic pressure to the lower rudder, okay? And it's only the lower rudder that has a load limiter on it, okay? Now what we would like is, when the flaps are extended, we would like to have increased responsiveness and authority to the rudder, so we will have higher pressure, which means a quicker response to the lower rudder, okay? And when the flaps are raised, we want to reduce that. We want to limit the amount of pressure to the lower rudder, so we'll call that the load limiter. And that's the purpose of it. Flaps down, full pressure, full rudder system pressure. Flaps up, reduced rudder system pressure, okay? So let's take a look at how that works. When the flaps are extended, we want, and this is just a for instance type number. It's not a full 3,000 psi, okay? But there is 3,000 psi worth of hydraulics in the system, okay, somewhere. What we're saying is, when the flaps are extended, we want the rudder pressure to be somewhere over here, okay? And when the flaps are retracted, we want the rudder pressure to be somewhere in what we will call the reduced range. Okay, we don't want the rudder pressure to be down to 0. We want it to be in a reduced range. Now the way the load limiter works is, there's a little eyeball looking at that reduced range. Okay, so let's draw, how do you draw an eyeball? Let's draw an eyeball. Okay, that's the eyelash. Okay, it's looking at that reduced range all the time. And here's what it wants. It says if the flaps are up, it wants to see the pressure in that reduced range. It wants to see that. If the flaps, okay, up, pressure in range. Pressure in view. If the flaps are down, it wants to not see the pressure in that reduced range. It just wants to not see the pressure in that reduced range. So, pressure not in view. And I'm pretending that it could see that little arrow. So if the flaps are up, if it sees that little arrow here, which represents how much pressure we have to the lower rudder, if the flaps are up, it's happy. If it does not see that little arrow, it's unhappy, and it lights up the light. Why? It assumes that the arrow's over here. Okay? Now, if the flaps are down, it doesn't want to see that little arrow. And if that little arrow is not there, it assumes that the little arrow is over here. Well, you can see that if it makes the assumption that if the arrow is not in view, the arrow is over here. That's the assumption it makes. And that's why we call this a stupid light. Because it assumes, we'll call me the little arrow, okay? It assumes that if I am not in view here, I am off to this side here in the way of high pressure. But we all know that I could have been over here on the side of low pressure. You see? So, if the arrow were really over here, saying zero pressure, like what? Like if we lost all our A-system pressure. It does not want to see, if the flaps are extended, for example, it does not want to see reduced pressure. So will the light be on or off? That's right, the light will be off, even with no A-system pressure, if the flaps are extended. Why? Because it does not want to see the pressure gauge right here in the reduced range. Very good question. How would we have gotten the flaps down without A-system? You're getting ahead of me, okay? We would have used our electrical switches, okay? Very good. Shows that you're thinking. You are paying attention, aren't you? I mean, this tape costs you a lot of money, right? Okay. Okay, if we lost A-system pressure then, and the flaps were up, would we have a light or not? That's correct. We would have a light because the pressure would be over here. Flaps are up. The arrow would not be in this range, would not be in view, so we would have a light if the flaps were up. If the flaps were down, we would not have it. We would not have a light, and we would not have a load limiter. But in reality, we have the standby rudder, which is full pressure, so we do not need a load limiter light, do we? If we've lost A-system and the flaps are down, the standby rudder is operating at full pressure. So really, the light is still telling us the truth. For the wrong reason, but it's telling us the correct thing. When the flaps are up with a loss of A-system, we've got the standby rudder probably turned on, which is full system pressure, which means, hey, take it easy because you could over-control. And when the flaps are down, we've got full system pressure to the lower rudder, again through the standby system, and it's saying, hey, no problem. So I guess you could say that although this is a stupid light, it works correctly even when you lose A-system. Okay? The only reason it's even worth mentioning in so much detail is why? Well, when you walk out to the airplane and do your system, your panel setup, you would like to know what that light is saying and if it's telling you the right thing. And if it's telling you the right thing will depend, of course, on whether the flaps are up or down and if System A is pressurized or not. It would be very unlikely for System A to be pressurized, though, when you walk out to a static aircraft. Okay? Now that completes our discussion of the second officer panel, but I would like, for a minute, to talk about the APU and the dump system. These are on the second officer auxiliary panel. First, we'll talk about the APU. Now, you're probably aware that the APU is kind of added as an afterthought There are 727s in the world that don't have APUs. And the APUs that were added on the short-bodied airplanes were just plugged in, and they used the ducting that happened to be there for the wing anti-icing system through some clever arrangement of some valves and things. Later airplanes, the stretched and advanced airplanes, have their own pneumatic ducting for the APU. Okay, we've got an APU generator, which has its own field breaker and generator breaker, just like the airplane generators have. We've got, instead of a kW meter, we've got an AC ammeter to tell us the load. And that ammeter, by the way, will reflect the load used by external power as well as APU if external power is powering the airplane. Now we've got an exhaust gas temperature gauge. All we need to know about that is the max allowable temperature is the red line. We've got a 3-position toggle switch labeled off, on, and start, and when we go to start, we start an automatic starting sequence. We don't have to do another thing except leave it in the spring-loaded on position. And we will get a crank light on our lower annunciator panel. When everything works properly, the engine will go through a complete starting cycle. We can monitor the status of the engine by looking at the volts and freaks, the output of the generator, and when that is stabilized, it means the APU is up to speed. Instead of a fluid coupling on the constant speed drive, it's a mechanical coupling. Actually, it's not a constant speed drive. And when the APU slows down, we're going to have a loss of frequency. The APU has its own fire protective system. We've got a fire warning system that works virtually identically to the fire warning and protective system on the engines themselves. And we're going to be discussing that during the next hour. I do want to discuss what will happen in the event of some problems with the APU, however. What if the APU starts to slow down? What if the APU cannot provide the full electrical and pneumatic load for the airplane that you're demanding of it? What happens? Well, nothing very much gets hurt if you start to cut down on the flow of air. But once you cut down on electricity, you can burn out a lot of electronic components. So it gives priority to the electrics, okay? If it can't meet both needs, electrics gets priority, okay? There are several times that the APU will shut down on its own. You'll get an automatic shutdown if you get an overspeed, a loss of oil pressure, or if you get a fire. And in addition, you'll get an automatic slowdown, and it may all the way shut down, but it's not an automatic type thing, okay? It may just slow down until it can't go any slower, and then it might quit, for an excessive EGT. In other words, it will start slowing itself down to keep the EGT within limits, and it might have to slow all the way down to nothing, to dying. Okay? One significant difference is that between the fire protective circuitry on this and on the engines is that the detection and protection are both on the battery bus. And you'll see in a few minutes that the engine fire detection and protection are a little different from that. Okay? We get our fuel for the APU, as I mentioned briefly in our engine fuel system discussion. The fuel for the APU comes from the number 2 fuel tank. This will complete our discussion of the second officer's panel, and now we'll go to the forward and overhead panels.